Okay, participants, good afternoon. Welcome to this second session. For this session, we have with us Dr. Biranchi Panda, Assistant Professor in Department of Mechanical Engineering, IIT Guwahati. Uh, Sir is a alumnus of this particular university, that is BSSUT Burla, and he did his PhD from NTU, Singapore. He has H-index of around 21 and more than 1500 citations. So his research area is basically advanced manufacturing and design, 3D and 4D printing, modeling and characterization, energy and sustainable environmental technologies. So we are fortunate to have him with us for this particular session. Sir will be speaking on 3D printing future homes from project to product mindset. So I welcome you, sir, to this particular session, and we can start it now. Please, sir.
Okay. Thank you for the introduction. So I hope my screen is visible, right?
Yes, sir, it is visible.
Okay. Once again, thank you for the introduction, and thank you for inviting me for this lecture. So basically, okay, now I'm a mechanical engineer myself, Dr. Biranchi Panda. I'm an assistant professor of mechanical engineering at IIT Guwahati. So as you know that I am also an alumni of BSSUT Burla. I completed my PhD, my BTech in the year of 2012. Then I was doing my master at NIT Rourkela, and that time I got an opportunity to work in some research problem in Portugal under Erasmus Fellowship. So after completion of my MTech, I joined Nanyang Technological University, Singapore to continue my PhD. So during my PhD, I was working on a project called 3D printing future homes. Okay. So though I'm a mechanical engineer, but I'm going to say today why I'm so much interested in printing the homes and what is its importance. So in this lecture, I'm going to briefly introduce about my PhD work and my recently whatever current work I'm doing at IIT Guwahati. Hopefully, you'll find some new insights. I was also working in metal and polymer printing, but I thought this topic of concrete or like home printing will be more interesting to you because there are not so many researchers working in this area. So when I started this project, I had a thought in my mind that nowadays every contractor, even people of India, like when they wanted to create their home, there are so many constraints. And so I thought, why not let us print the future homes and move from the project mindset to a product-based mindset. Because being a mechanical engineer, I know that those automobile companies, they are using now a lot of robotics, IoT devices, automation, digitalizations to produce those automobile components. Even the cars, those that you can see in today's market, they are being fabricated in the company in a very rapid manufacturing processes. All the robotics are assembling all the parts, and finally you will get a car. And tomorrow, if you want to purchase a car, you have to go to the showroom and have to select, okay, I want this model, you need to pay, and then the car should be yours. So I thought, why not we can implement the similar mechanism to print a home instead of making it project. Project means now if you want to create a home, you need to get a land, you need to get a contractor who have to fabricate, you need to purchase the raw materials. So instead of making a project, why can't we move into a product-based mindset and we use the digital fabrication technique like 3D printing to print the entire building and ship it to the customer. So that was our main goal. So with that thought, we started working on 3D printing of concrete-based material. So today I am going to share my research with you students, and then we'll have some interactions. What is your inputs and how we can move this technology to print future homes in India. With this introduction, I would like to start my talk. So those who are not from civil engineering background, for them I have put only 2 slides for defining the concrete. It's a very simple material. So we just need to mix cement, sand and water. So when you make concrete, we need to create a glue. So the glue comes from mixture of cement and water. So when cement and water mix together, it forms a glue. And then when you add these stones or sand particles, this glue try to bind them and it will make them concrete. So this is the basic definition of concrete material. Now, if you want to create a structure using concrete, so what is the basic step? Normally, like in casting, we create the mold. So similarly, in civil engineering also, we create the mold to erect any structure. So as you can see a picture on my screen, that some workers, they are trying to assemble the mold, and once they assemble, we need to dump the concrete, and this mold, or it is called formwork in civil engineering. So once you assemble the formwork, we have to dump the concrete material, and after it hardens, we can remove these formworks and we will have our own final structure. So this is a very conventional way of fabricating concrete structures. So what are the problems here? So when we found a very interesting statistics that over the past years, the productivity of the construction industry is quite stable. It is not improving or increasing compared to other manufacturing industry. Then we decided, how can we bring more digitalization to automate the fabrication process in construction so that we can print our future homes more efficiently and make it also quite affordable. So since we come up with the statistics that the productivity in the construction industry is not improving over the years, and we started to do investigation, what are the main causes behind it. And then we realized that lack of automation or digitalization is one of the key barriers for improving the productivity in the construction industry. Apart from that, since we know that the building structures surrounding us, it is mostly made of concrete material, and concrete, especially the cement that we use to create concrete, it is also responsible for the global CO2 emission. So that is also main problem when you want to create something with concrete material. The third problem what we see in construction, that the laborers or the workers, they are working 24 day and night, and they are exposed to an unhealthy conditions which is not good for their health. And sometimes these workers who create your buildings, they are exposed to a very risky environment. And with this kind of thoughts and background knowledge, we started to think that how we can implement a digital technology in creating those buildings so that these laborers or the workers who are working in this field, they can be shifted to a high skill job. So for that reason, we started to working on 3D printing of cement or concrete based material. So why to print concrete? To answer these questions, I have two key points. The first benefit of printing concrete that I can see from my perspective is the design freedom. I hope all of you know about this feature of 3D printing, that we can print any complex geometry, and we don't need the mold to create such complex structure. So similarly in 3D printing also, we can create a very complex structure. We have the design of freedom. This picture I borrowed from a French company who were printing concrete. So you can imagine the degree of complexity that is involved in this picture, and I am sure that it is very difficult, or I can say it is impossible to create such kind of structures using conventional casting methodology. So the first advantage we get by printing of concrete is design freedom. We can print any design and we do not require any mold to create those kind of structures, because as you know, in 3D printing we deposit the material layer by layer. We just need the CAD model of the structure. Once we have the CAD model, we can directly print it, and we do not require any mold to erect this kind of structure. The second reason, which is most appealing to me, is all about sustainability. This keyword is very important in nowadays. Being a manufacturing engineer, initially my focus was on creating different manufacturing methods, especially in the mechanical domain. But later I realized that it is not only about not only production unit, but also we have to now take care of the sustainability aspect of any manufacturing process. Yesterday I was reading one article that was published by World Economic Forum, that in future sustainability or recyclability can be considered as a law of our society. It means every manufacturer, when they are producing any item, now they are responsible also to recycle the waste material that are being generated during the manufacturing. So then later I shifted my research focus towards more sustainability, recyclability, which can be really helpful, because now we know that during manufacturing, lot of waste being generated, and that create pollutions, and it creates lot of other problems in our society. So then I shifted my focus from manufacturing to recyclability. How we can recycle, how we can develop a technology to reuse those waste material that are being generated in the manufacturing process. So specific to concrete printing, how it is important. So when I talk about sustainability, we have two aspects when we want to print concrete. Whether our material that we are using, is it sustainable material? Yes or no? The second question, whatever structures we are printing, is it a sustainable structure? So two important points are here. So to answer these questions, I will say definitely we are trying to bring more sustainable material in the manufacturing of this concrete structure. And talking about sustainable structure, you can see there's an example of this 3D printed bridge in Netherlands. And most surprisingly, if you see the bridge cross section, it is not entirely solid. Rather, the cross section has been topological optimized. There are some lattice structures that reduces the weight of this bridge. It also saves concrete, and thereby I mean it is a sustainable structure, because with the 3D printing technology now, I can deposit the material where there is a need of strength. I don't need to put the material everywhere, because now as a design engineer, I know I can topologically optimize the structure in such a way that it can still take the load, but we can have a reduced mass of concrete instead of a bulk of concrete. So this kind of topological design structure can be easily printed by the 3D printing technology. So this technology can give us design freedom, it can give me sustainability, and apart from these 2 points, 2 critical points, automation, digitalization are definitely with us when we are going to print any concrete structure. So this industry is a very big industry. It contributes to 6% of global GDP. It's a $10 trillion industry. But if you see very closely, the construction projects are mostly 20% over time and 80% are more costly. Today, if you want to have your own building, you go to the builder, they will say some price, suppose X. You go after 2-3 years, or if sometimes it happens, they estimate the time duration of your building, but it cannot be achieved in that time duration. So sometimes due to overtime, the building prices become more expensive. So if you look into this reason behind all these price fluctuations over time, you can see that we have very less automated devices that are being used in our construction. But if you see this percentage of robotic system that we are using in our constructions, is only 0.2% robots are being used. So having said that, there are so many advanced equipments that our construction people still are using. We have some machines that can simply lay down the bricks. We have some machines or a factory of future, where, as I mentioned in the beginning, that we can create the entire building. It's an example of precast companies who are entirely building the structure, and once it is ready, it can directly ship to your place and you can install it and use it. It's a very simple and affordable way of making concrete structure. Everything that you need, you create in a factory, and then once it is ready, you can directly install it on site. So to track all this progress of this construction planning, management, costings, we have been also using an advanced software called building information modeling, where all these progresses are being captured. So recently, as I was mentioning, the World Economic Forum, they presented the scenario of future of constructions, where all these automated techniques will be connected to internet through IoT devices. If you closely look into this picture, you will find that 3D printing or additive manufacturing is also being considered as one of the future technology that are going to be implemented in construction sector. So let us come to 3D printing of concrete structure and understand how it works. So before I start 3D printing of concrete, let me play a very short video. This video is almost 80 years old video. Okay, but you can get in feelings of concrete printing just by going to this video. Let me play it for you. I hope you are able to see it.
On October 20th, 1941, he applied to the U.S. Patent Office for registering a patent for a wall building machine. The person whose time was devoted to the invention of equipment for the food industry is the author of the first building 3D printer. He created a prototype.
Yep. So you can see that 80 years back, these people there also know 3D printing. They can create some structures using a machine that can deposit not concrete, something similar to soil or mud kind of materials, but layer by layer. So after 80 years, if you look the same scenario, it looks something like this. This is a company, Episcor from Russia. It claimed that they have an advanced 3D printing system and they can print the entire building in less than 1 day. So just by showing this picture, I'm not dehumiliating any companies, but at the same point, I would like to mention that in just 80 years of time, we just improved our mechanical machine. So the machine that they were using, I think they have some less degree of freedom. But if you see this kind of crane kind of systems or robots, we have more degree of freedoms. So in terms of machines, instruments, we have been improved, but the technology remains same. So still now the construction industry is adopting this kind of technology. We started working with this concrete printing technology. So I'm just going to show you one video. So before that, just have a look on the schematic of this concrete printing research. When I started my PhD in 2015, there's a lot of interest from both academia and industry to work on this topic, because the industry were trying to adopt this technology, because somehow they found this technology can make us creating affordable homes compared to a regular casting methodology. So this is the video of concrete printing. Let me play it. So it is similar to an FDM based technology. Those who are having 3D printing background, they can easily see that it is similar to fuse deposition technique, where we are depositing the concrete layer by layer. It's similarly like in FDM process, we deposit the molten plastic layer by layer. Here we don't need to melt it, but the concrete by its own nature, we can mold it and we can deposit it directly from the CAD model. So the process starts with CAD model. So this is the printer we have used to print this structure. It is a customized machine, because when I started my PhD, there is no machine available for printing of concrete. So we made our own machine. It is a 4-axis gantry printer. X, Y, Z axis are visible, but the rotational axis that you might have seen during printing of this structure, the nozzle was rotating. So that we count as a 4th axis. So this is a 4th axis gantry kind of printer. On the left hand side, we have a controller. Once you create the CAD model, we need to slice it according to some layer thickness, and then the G code have to be dumped into this controller, and this controller is going to control the entire machine to print the concrete. But who is going to provide you the material? So for that, we have a pump that you can see on the right hand corner side of this picture. This pump is used to pump the material to the nozzle. So there is a connecting hose pipe through which the material will be transferred from the mixing chamber to the nozzle, or you may call extruder. And then this controller is going to control this machine to deposit the material layer by layer. It's a very simple process, but let us see what are the challenges when you want to print such kind of material. So these kind of challenges are very common, even if you deal with your fuse deposition modeling technique, or I may say in generally all kind of extrusion based 3D printing process will be having the similar challenges. So as you can see the picture on my screen, when you print the first layer, or we call it as a filament, when you print the filament, it should not spread away, because if it's sprayed away, it is not going to maintain its shape. So what do you mean by maintaining shape? So normally we use a nozzle to print the structure. So whenever we're printing, this material should retain its shape according to the nozzle diameter. Suppose I am using a nozzle of 20 mm diameter. So when I'm extruding the filament diameter should be almost similar to the nozzle diameter. It should not be more, it should not be less. But if the material design is not proper, once you deposit, the material will simply flow away. So it happens because of the low yield stress of the material. Now I'm connecting some engineering technical term to this process. So when the material is going to have low yield stress, the material, once it is being extruded out, it can simply flow away. But definitely we do not need this kind of property in our printing process. So with some chemical modifications, what we can do, we can slightly create a more stiff mix for this printing application. So when you make it more stiff, we'll see that because of high viscosity, the layers will be discontinuous in nature. It will not be continuous. When you are printing, it will be fragmented. So neither we need the material to have a very high yield stress or viscosity or low yield stress, because when you're having low yield stress, it will simply flow away. It is not going to retain its shape. And when it is going to have high viscosity, you will get discontinuity layers. So we need to have an optimum material combination so as to print the material. So we have to properly create a balance between yield stress and viscosity, and thereby we have to come up with a printability window where these mixed combinations will be printable. Okay. So when I say printable, it means the material should be extrudable, maintaining its own shape, and buildable. We need to also deposit more layers. Okay. So how it can be done? So normally for our regular construction, we use Portland cement, or we know it's a cement. So cement have its own mechanism to create such kind of texturotropy material. I am not going to explain this complex keyword, but I have some supporting slides. In the subsequent slides, I'll explain it in better way. So cement has a property where if you simply use cement, you can deposit some material, and to deposit more layers, you need to always control the yield stress of the material. But our goal was to create a more sustainable mix design. So when we wanted to create more sustainable mix design, we tried to identify what are the waste material that are available near us. Then we came to know that we have a power plant that produces fly ash, and when we look the fly ash under a microscope, it looks like a spherical ball. And then we try to replace this cement, because as you know that cement production is an energy intensive process and it emits lot of CO2 to the environment, which is not good because it is causing the greenhouse emission. So we wanted to replace the cement partially with the fly ash because it is an industrial waste, and we also wanted to create more sustainable mix design. But as I said that whenever we saw this fly ash under the microscope, we can see that they are like spherical balls. So what is going to happen when you want to replace cement with fly ash? Because this is a ball kind of a spherical particles, so they have a high tendency to roll over. They can easily flow away. So ultimately, when you replace cement with this waste material called fly ash, which is having spherical particle size, they can be easily flow away. So after deposition of 3-4 layers, the whole structure is going to collapse. As you can see in this video, that because of the high flowability or low viscosity, this structure is going to collapse. Even we tried other structures, after printing a few layers, the whole structure is going to collapse. So to improve this problem, to improve this material combination, what we did, we tried to take the help of nanomaterials. Nanomaterials, though they are nano sizes, but they can do a very wonderful job. So we use a customized nano clay. We made this nano clay. So what happens in this nano clay? We came to know that just by adding 0.5% of this nano clay mix, it can improve the yield stress or viscosity of the material 5 times compared to the control mix. So significant improvement we have found when we added this nanomaterials to this fly ash mixed concrete. And we investigated what are the causes, why it got improved, and then we came to know that there is a mechanism called flocculation, and because of that, these nanomaterials, they are able to improve the yield stress of my control sample. The sample that I printed, it collapsed. Now the same material has more yield stress, more viscosity, but still it is in printability zone, means I can print it without any discontinuity. So there is a mechanism I'm not going to explain in detail, but flocculation mechanism is happening here, and it is providing the material with higher yield stress and viscosity. Okay, so what happens, let us understand the process in more detail. So during printing, we initially start with a mix, which is at the mixer, means once you mix the material, it is at the mixer. Now we need to pump it, because the material need to be traveled from the mixing point to the extruder or the nozzle. So the next stage is extrusion, where we have a pump and we are extruding the mix. So after extrusion, we were depositing it. So there are basically there are three stages in this printing process. One is rest, one is extrusion, one is deposition. Also it is counted as under rest, because once you deposit the material, it is in rest condition, but with time material are being loaded with new layers. So there is slight difference between the first and last stage. Here the material remains and entirely in the resting condition, but in the last stage, though we are depositing the material, it is not purely in resting condition, because we are keeping adding the layers. So the materials in the bottom layer, they are exposed to some stress because of the top layers. So now if you see this process more carefully, you will see that we need a material which can behave like a solid before and after deposition. Means we want a solid kind of behavior so that this material can hold more layers. But in the middle stage, that is during the extrusion, we need the material to be very flowable, because otherwise it is going to create problem during pumping. So it is a bit contradicting property. During pumping, we need the material to have low viscosity, but after pumping, we need the same material to behave high viscosity. How it is possible? We have to make it possible for printing of cement or concrete based material. So that was the main challenge while developing the material. So, but as I mentioned, with the help of nanomaterials, we were able to print more layers without any deformation. So when this concrete printed layers started to deform, we classified their deformation. Again, we took the help of strength of materials. Okay, because every time when we play with new system, new material, we always try to connect with fundamental mechanism. It may be from strength of materials, it may be from machine design. So we categorically say that the deformation process in the beginning, it is elastic deformation, but once the material crosses its own yield stress, we expect the material to have plastic collapse. And to measure this deformation, we have modified our printer. We attached a laser sensor to this extruder, so that during printing, this sensor is going to measure the deformation of the layer. This information is really helpful because we developed a feedback control system. So when the material is going to deform, this laser is going to give me real-time data, and with that real-time data, I can optimize the material design, I can optimize the printing parameters in such a way that I can reduce the deformation. Okay, so this is again like something like on process control, how we can further improve this process controlling so that we can accurately map what is happening during printing, what are the changes happening because of the material, because of the machine. If we are able to capture it, we can design a better material, we can design a better machine for printing a very tall structure. So that was our goal. So for that, we have done some modification at the printer level. Then we are able to print the material. But just now I have discussed with you that during printing, there are basically two stages, right? One is during extrusion and one after deposition. So during extrusion, we need low viscosity material, and after printing, we need high viscosity material. How it is possible? It is possible when you can design thixotropy material. What is thixotropy? To explain this concept, let me show you a very simple example. Early morning when you go for your brush, you used to squeeze the toothpaste, and this paste, it easily comes out of the tube. You hardly apply any small, like some pressure to extrude this paste from the tube. And more interestingly, if you see that once this material extruded out from the tube, the toothpaste tube, it remains its in original shape. It never deforms unless you apply some more pressure. If you simply extrude it on the brush, it remains in its original position. It never deforms. But you apply a very small pressure to extrude this paste out of the tube. So once you apply pressure, it can easily extrude out from the tube. But once you release the pressure, it remains in its own shape and position. So this is something called flexotropy. Means once you apply some high shear rate, the material will lose its viscosity. So when you are squeezing the tube, the material is subjected to some high shear rate, and this paste can easily comes out of the tube. But as soon as you release your force, the material can recover its viscosity and remain its in own position. So this toothpaste development is also a very research R&D problem. It's not that simple. So they also try to develop the exotropy material for this toothpaste application. So we also want similar property in our printing because we are pumping. So during pumping, we are applying some shear rate. So with the shear rate, we expect the material to lose its viscosity so that it can be easily pumpable, it can be easily extrudable. But once you deposit, once you remove the shear rate, it should remain its own position without any deformation. Okay, so how to measure the exotropy property? It's a very simple process. We developed two protocols to measure this property. So just now I explained you 2 points. One is you have to apply some the pressure, and when you apply some pressure, force or shear rate, the material loses its viscosity. The material gets breakdown. So first we classify the protocol name as structural breakdown. It means we'll see that how different mixed design can be breakdown under certain shear rate. So for that, what we have done, we develop this protocol of testing. So where we apply high shear rate and see how first the material can be breakdown. So for that, we can see that from this image that there is initial shear stress, and once it completely break down, we have the final shear stress. If you take the ratio of this, you will get an index, and this index is responsible to tell you how fast you can destroy your material. It is important because if you remember the 3-stage process, during extrusion, we need the material to be break down very easily, so that we have to apply low pumping force or low pumping pressure to extrude the material or to deliver the material to the nozzle. So this protocol or this index is going to help you to select your final mix design, which requires less pressure for extrusion. Now, since printing is not about extrusion, we need to deposit more layers. So now let us come to the third part of the test, that is called viscosity recovery. Because during pumping, you might have applied very high shear rate and material completely loses viscosity. Now, if the same material will be deposited, we cannot print more layers because this high shear rate during pumping, it completely loses its viscosity. We now need the same material to recover its original viscosity, then only we can print more layers. So for that, we conducted viscosity recovery test. In this test, we investigated that after pumping or after your extrusion, what is the material state of the art. So for that, we conducted the viscosity measurement at 3 intervals: before extrusion, during extrusion, and after extrusion. Then we can see from this graph that before extrusion, when the material was at resting condition, it has high viscosity, means it can still be in stable position. So during extrusion, when you applied high shear rate, it completely loses its viscosity, and the value, if you see, it completely below between 10 pascal second. So it is a very good material. You have to apply very small pressure to extrude it. But now let us see what happened after the extrusion. So after you extrude it on the print bed, the material has the capability to recover its original viscosity. It means now during extrusion, though it loses its viscosity, but after extrusion, it has the capability to recover some around 80 to 90% of its original viscosity. So it is still well and good for our applications. We can deposit the material without having the behavior of flowability, because during extrusion that the material completely lost its viscosity, but after extrusion it can recover its viscosity, and with this high viscosity we can print some layer without any deformation. So whatever material we develop, we have printed more than 60 layers, and this is a very tall structure that we printed for our one of the project. That project I am going to show at the end of my slides. So this is all about material development. Then we wanted to do some more experiment on the machine perspective. Okay, so that time we came to know that there is a competition by NASA. So they wanted to develop a material to print habitats, or you may call homes, for the astronauts that they are traveling to Mars or Moon. The requirement was, how can we automate that or digitalize this fabrication process? But the condition was the material should be developed in such a way that it should need less water, because in those environment we don't have the availability or we don't have the freedom to use lot of water. So the key criteria was, let us develop a material that needs less material, less water. So for that particular applications, we developed geopolymer material. So again, it's a more complicated matter. So I'll quickly skip this slides. But before I skipping, let us give me a very small, a brief introduction to this material development. So here we used some pliers, GBS, and some basalt material that we came to know that similar composition was available at Mars. So that information was provided by the competition organizer. Then we used some basalt kind of material, and we make sure the compositions are similar to the material that are available at Mars. And then we created this geopolymer mix, where the activator or the chemical component, because here we don't need a lot of water. Instead of water, we need an activator, that is potassium silicate, and we use this potassium silicate to make the concrete material, and that too using all the byproducts like fly ash, slag. Those are coming from the different steel plants. And we investigated to how we can design a printable mix design using this material. And then we realized that the activator that we are using in our process, it is the main culprit, because the activator are available in different concentration, or you can say different molar ratio. So different molar ratio of activator has different viscosity. As you can see in this picture, if you take 1.8, it has low viscosity. If you go for 2.0, it has high viscosity. So the activator viscosity is controlling the viscosity of my final material. So as you can see on the top two pictures, different viscosity of the two materials has been recorded. When you are going to use the activator of high concentration, you are going to end up with a material of high viscosity. So when the material viscosity is good, you can print a very well stable filament. But in case of 1.8 molar ratio, since the viscosity was quite low, we can see that after extrusion, the layers are simply flowing away. Okay. So then again, we took the help of nanomaterials. We improved the material combinations by changing a lot of parameters. We did a lot of chemical tests that I don't want to explain in this slide. But what is the key improvement that we have found? That during printing, if you don't use any nanomaterials, or simply if you use the control mix after printing of some layers, you will see some deformation. But with improved material combination, we can see that the material is not deforming, because there is no gap between the extruded tip and material. In the initial picture, you might have seen there was a gap between the top layer of the material and the nozzle. So, but in such cases, we don't have any gap between this nozzle and the material. So it means my machine is moving in according to the G code, and material is not slumping at all. So again, we did those kind of texturotropic characterization, and we printed some structures to make sure that we are able to print this material up to certain height. So this is the video that we sent to NASA for the competition. I hope you can see it. Yes, so as you can see that in this application, we wanted to use a robotic system, and accordingly the program was made because we thought that in that very harsh environment, we should not use a gantry system because it needs a lot of installation, but a robotic system that was mounted on a movable platform can be more effective in such applications. So again, the same material was printed of 60-80 layers to demonstrate the material is still printable without any deformation or defects. Okay, so now this was all about material development, but when we are targeting to print affordable homes, the situation is quite different, because for printing homes or tall structures, we need to again redesign the material in such a way that we can print 2-3 meters tall structure. So for that, whatever material development we have done here, we need some slight modification that is highlighted in this picture. So it tells that when you want to print tall structure, you have to now use the concept of FDM printing. It means that as soon as you deposit the material, it must be hardened so that you can deposit more layers. Because if you want to print 10-20 layers, you may not have to harden the material quickly, but if you want to targeting to print 2 or 3 meter tall structure, we have to find some mechanism so that this complete printing system can be made in such a way that once you deposit the material, it will quickly harden, and then you can deposit more layers. So how it happens? So you can see the schematic of the 3D printing system. So what we do at the extruder, we try to add some chemicals. We call it accelerator. So they usually do some changes in the material chemistry and try to create a rapid hardening mix. So once you deposit this rapid hardening mix, you can deposit more layers. You don't have any fear of collapsing the entire structure. Okay, so this is an example by a different university. So this is how the mechanical nozzle looks like if you want to extrude rapid hardening mix. It has 2 inlets, one from the regular material, that is the concrete. The second inlet is for adding the chemicals. So here they have developed a smart extruder device, so where can mix 2 materials and extrude the rapid hardening mix. It is important when you want to, or when you are planning to print tall structures. Okay, but we later realized that when you are printing these tall structures, the material is subjected to compressive strength, and for that what we have done, we have modified the tensile compression test that regularly we do for any solid material. So instead of solid material, we try to put a fresh material. This material is very fresh, and we try to see how much load this material can take with respect to different time. Because you have to be very sure that when you are printing tall structure, at every point of time, the material is changing. So we also wanted to capture the material behavior changes with respect to different time. So we initially took the press mix and we compress it in 5 minutes. Then the same test was repeated after 150 minutes. Because we know that if we are planning to print a tall structure, we'll be still printing the material after 150 minutes. So we wanted to see what changes is happening to our material once it crossed 150 minutes. So for that reason, we conducted this green strength test. It's called green because the material is very fresh. You can see at exactly 5 minutes, if you compress, it is going to deform very easily. But if you wait for 150 minutes, the material slightly get hardens and you'll get a shear crack if you test under compression. So we capture this material behavior with respect to different time interval. Then we did some direct shear tests. So the shear test is going to give you a property of shearing property of the material. So the compressive strength and shearing strength, we try to develop a model in collaboration with another university in Australia. And this model is very helpful because now we have a tool to predict when the material is going to collapse. It's very useful because when you are printing for a tall structure, 3 meter, 4 meter, if after completion of 2 or 3 meter, the whole structure collapse, it is going to be a nightmare. So for that reasons, we initially developed this kind of modeling or the simulation tool, so that can be used to predict before you print when the complete structure is going to collapse. And this information is useful because accordingly you can design your material or you can set your printing parameters so that you can avoid this collapsing of structure. So let me show this video. So how it has been done. Yes. So now I think you get a complete idea that how this deformation takes place. So initially, when the materials are at first stage, elastically some deformation happens. But when you are adding too many layers and it exceeds the material strength, it simply go into the plastic collapse stage. So this has been modeled using this, I think, some commercial software. So now with those material background, we thought, okay, let us now work on machine sides or printer side, because anyway we're being mechanical engineering side. Let us do some experiment with the 3D printer process parameter changes. So we came to know that when you are printing concrete, like other 3D printing process, we have some process parameter like printing speed, layer height, nozzle shape. So all these process parameter, it really affects the process quality. So if you see that we have been printing this material with different printing speed, with keeping the flow rate constant. So when the flow rate was constant, and if you change the printing speed, you will find an optimum printing speed at which the layer width, dimensions, everything will be similar to your nozzle dimension. And we count that is the optimum speed, because for other speeds, either there will be over deposition of material or there will be less deposition of material. Okay, so for that reason, so we conducted different printing speed experiment, keeping the flow rate constant, and we try to identify for different material what is the optimum printing speed so that these layers will not be deformed, or there will be no extra or less material in this filament. So as you can see that printing parameter also has some impact on the filament property. Next, what about the nozzle shape? So regularly in printing, we use 3D printing. Normally we use circular nozzle, but you can see that if you are using a circular nozzle, then we are going to have a lot of porosity in our structure. So here the science of combining material process parameter comes into picture. It means that if you want to still use circular nozzle, you can able to reduce this porosity by changing the material behavior. What does it mean? It means that even if you want to proceed with circular nozzle, you make the material slightly low viscous, so that when the layers will be added, they'll be slightly added together and you can reduce this micropores. So it means that only printing parameters are not responsible for producing quality printed structures. We can also play with the material as well as with the printing parameters. So first picture represents when the metal is very stiff and still you are using circular nozzle. In the second case, you can see that the material has been slightly modified so that with the loads of the layers, this pores has been reduced. But apart from all these things, if you are going to simply replace the circular nozzle with the rectangular nozzle, you can further minimize the pores, as you can see on the last picture. So this is the all about effect of nozzle shape and size. Okay. Next comes like all about printing design, because just now I discussed the connection between material and process parameter. The third important property that again are related to these two property are design. So what I want to conclude that in 3D printing, your material, process parameter and design, part design are all correlated. You cannot simply optimize one parameter and expecting best result. It is not possible because all these three things are interconnected. So how? Let us see this example. We wanted to print a toilet with 1.8 meter height, and when we designed this toilet unit, we found that we have a corner at some section. But now we wanted to print this corner. There is now argument of what is the best radius. So as you can see, for a very smaller radius, we will be having some tearing effect on the layers. If now I increase the radius of curvature, those tearing effect will be nullified. So it means that here I am not talking about material, I am not talking about the process parameter. Rather, the design of the structure is very important and it can severely affect the property. As you can see, if we want to make it a very small radius of curvature, you will be having a tearing effect. But again, as I mentioned, this problem can be solved if you can optimize the process parameter or the material, because these three things are related: material, process parameter and structure. So now keeping the same structure, if I want to avoid this kind of tearing effect, what I have to do? I have to make the material slightly more soft, because it happened because the material is very stiff. So when you take a sharp turn, it is going to have a tearing impact. Now if I make the material slightly soft, I can go with a slow speed. This effect can be minimized. That is one possible way. The second way, you simply change your design. If you can see that if I increase the radius of curvature, I can solve the issue of tearing impact. Okay, so ultimately we came to a conclusion that in 3D printing, your design, process parameter and material combinations are very much important. And finally, when you print everything, we have to go for mechanical property test. So what we do, like in 3D printing, as you know that the parts that are being produced by 3D printing are not isotropic, it's behaving as an anisotropic. It means that they will be having different property in different direction. So to confirm that, what we have done, we have printed the sample and we have collected different cubes, because these are the standard cubes for testing of compression. So we extracted the cubes and we applied forces in three different directions: F1, F2 and F3. As you can see, those loads have been applied in three different directions. But fortunately, we didn't see any kind of anisotropic. I will say it's not much isotropy, because you can see compared to the casting that is being mentioned as C here, the property in three directions are almost similar. Though there is a slight variation in the property, but almost this property are quite similar to the casted sample. But what is most important, but when you are going for 3-point bending testing, or in the bending testing, what happens that either the layers will be in this direction or it will be in the same direction of loading. So when the layers will be in the same direction of loading, another property comes into picture that is known as interface bond strength. Because as you know, in 3D printing, we are depositing the layers one by one. So the layer strength, the internal bond strength between these two layers are very critical, and it is going to severely affect for F1 direction. So for that reason, we started to investigate the tensile bond strength between two layers. So we printed the material, we investigated this property by changing the material, time gap, and process parameter. Suppose you are doing a very large scale printing. So you print one layer, it takes about 1 minute. Now for printing another layer, you have to wait for 1 minute. So it means the time gap between these two layers is almost 1 minute. Similarly, if you print a smaller object, the time gap can be reduced. So we try to investigate how this time gap is affecting the bond strength. And then, as you can see on the results, that with more time gap, the strength becomes very less. But what is again more interesting point here, that it also depends upon the material. If you are using a rapid hardening material, even some 10-second delay will create a very poor bond strength. But if you are using a material having some 10-20 minutes setting time, small delay of time gap can still provide you average tensile bond strength. So again here, the time gap is related to the material and process parameter. How process parameter affects this bond strength? For that reason, what we have done, during printing, if you slightly press the material, and if the material is slightly softer, these pores can be minimized, because these pores are the main critical points to create very poor bond strength. So during printing, if you can slightly optimize the process parameter, then these pores can be minimized and you are expecting a very good tensile strength in such cases. So again, I repeat, in 3D printing, every time we see that 3D printing parameter, your material design and structure, all three are interconnected. So with all this knowledge, we started to do some projects. Our first project was 3D printing of a toilet unit. So I remember it was a World Toilet Day, and we invited our Prime Minister to inaugurate this structure. This is a 3D printed toilet. So that has been printed in just maybe 60 to 1 hour. Normally, if you do casting, it takes 3 to 4 days to have this kind of structure. And we invited our Prime Minister, and he also gave a very good comments, and he also appreciated our work, that this kind of digital construction technology can really provide affordable or timely structures for many reasons. Okay, the next project we did is all about 3D printing of bathroom unit. So that was the key topic of my today's talk. So when I talk in my first slide, I told that we want to now move from project-based to product-based technology. It means now if you tomorrow want to create a building, you should not wait for the land, you should not wait for the construction, you should not wait for the local constructor to bring you the material to erect everything. Now, what we propose with the digital technology, we can create the entire structure in a factory, and you have to come and select, I want this kind of structure, and directly it will be installed on site. So that is called more product-based approach instead of project-based approach. So to satisfy that goal, we try to print a bathroom unit, because in Singapore, all the buildings has been fabricated off-site. They don't create the building in on-site. They create in the off-site, means in a factory, and then they install it on-site. So to have a 3D printing effect in that process of construction, we propose, let us print the complete bathroom unit, and then we can install it on the building site. So for that, we purchase a new robotic system, and now it is being used to print this 3.2 meter tall bathroom unit. And after printing, we have fitted all the facility, and now it is ready for testing and installation. So this is the complete bathroom unit that has been printed using the robotic system that you can see in this picture. So I have one video, hope you can see the complete process here. Yes. So now, as you can see, that after printing, the structure has been tested at our building construction authority for many other tests, because they have to provide the authority to use this kind of structure in for any building application. So now, if you see these 3D printed structures, they are more like lattice kind of design. So it makes the entire structure more lightweight, and you can also save a lot of concrete uses while you are printing this kind of structure. So now the main problem or the main challenges, that is all about reinforcement during 3D printing. So we know that the concrete is a brittle material. We need to improve its ductility property. For that reason, what we have done, we have tried to find a nozzle design in such a way that it can enforce the reinforcement, that is the steel cable in this case, during the printing. So now this nozzle is going to deposit the steel cable along with the material during printing. So once we printed this material, we expecting, or we got a very good result in terms of load versus extension curve. So then somehow we're trying to reinforce this kind of steel cable reinforcement in our material. But in the literature, there are many possible ways. After printing, they are installing the rebars, or over the rebars, we are simply printing it. There are different approaches by which reinforcement has been added to this concrete structure. There are some research also. We have also printed some fiber reinforcement concrete. It's very easy. So we have to again optimize the mix design in such a way that this is the robotic system. So where we can print this kind of fiber reinforcement concrete just by adding the fibers. But again, since this is an extrusion based process, we found that these fibers are along in the printing direction. Once you print the filament, if you break it under the microscope, you can see, because of the high extrusion pressure, these fibers are always in the direction of the printing direction. Then with our some colleagues, we started to doing some 3D printing over the curved bed, because previously we printed on the flat bed. Now we wanted to print on the curved bed. So the same robotic system was used to print on the curved bed. So as you can see, that this bed is not a flat, rather it has been a curved bed, and the program has what we retain to print on such a curved bed and deposit the concrete. Okay, so now as you can see, whatever the structures we are going to create, it does not require any mold. If you want to create such kind of complex structure, definitely we need a mold. But now with 3D printing technology, just by reprogramming and properly designing the material, we can print such complex structure. And what is the applications? We are trying to create the building facade materials. Nowadays, you know, these facade materials are more like intelligent materials. They can absorb sun rays and they can provide powers to the building. So we thought, let us print this complex geometry, because to cast this element, it needs a lot of time to create the mold. So we can easily print these structures with our 3D printing setup. So sometimes when the structures are very big, we have to take the help of multiple robots, because these robots, sometimes if the structure is very big, these two robots can work together to print the entire structure. As you can see on the video, these two robots are working together. Okay, so that is also part of our automation technology. And then we again started to work on the more sustainable material. So there is a supplier from Australia who provided us this recycled glass. So they crushed the beer bottles and they provided this recycled glass in different particle size. And then just for replacement of the sand, we try to use this recycled waste product in our 3D printing material. So we optimize the combination in such a way that during the loading or after you deposit more layers, the material should resist more deformation force. So here the particle size is very important. So as you can see, this glass particles will look like angular particles. And these angular particles, if you optimize the distribution, we have done some simulation also to properly arrange this material in such a way that if you compress, they need more force to have a breakdown. Okay, so this is the material that we are testing, and we finally come up with an optimum mix design in such a way that these angular particles, they're arranged in a framework, it can take more load compared to sand. So now it has been an extra added benefit for using this kind of recycled glass. Sand is definitely natural, but now at some places we don't have availability of proper sand. So for those regions, we can use those naturally recycled materials, and we can simply replace with the sand for 3D printing application. And here the more interesting research is how you can come up with a plan so that this material can take more load compared to the regular sand mix design. So now I'm coming towards the end of my talk. I just wanted to show some construction 3D printing projects in the world so that you'll be having an impression that this technology can be really helpful in creating affordable and timely structures compared to our regular construction process. This is a company from Saibi. Now they are creating the building blocks in Dubai. So this is another company from Extreme. The same robotic system has been used, but they have designed a new nodal system where they can mix multiple materials and they can print more complex structures. So I truly believe that if you want to create those kind of building components using casting, it is much more time consuming and costly. And there are some designs that I believe it's very difficult or impossible to create using casting approach. But 3D printing has the capability to fabricate those kind of complex geometries. Recently, they have done a project for the municipality. This is the rain water harvesting unit. So they found previously they were casted it, but now with the 3D printing technology, they can make it more lightweight and they can print it in much less time compared to the casting. Another company, Basics 3D, you can see the level of complexity that they are bringing into construction using the 3D printing technology. This is like some furnitures. Some companies now, with the help of this 3D printing technology, they are now printing some urban furnitures like benches, tables, some showpieces for decoration purpose. This is the same company who claimed that they can print the building in less than 24 hours or 1 day time. The same company, they are now expanding their business in many different continents, and this is one of the latest project in the desert where it's difficult to go and work day and night. They have a 3D printer, and without the need of much more human intervention, this printer can print those entire buildings, as you can see, with the help of lattice structures. So there is no issue. I think they are now going for testing of this kind of building structures to get the approval from the authority. And this is the entire building that has been printed on a desert. And this has been done using the same company and their crane type printing system. In China also, they have also printed 2-story buildings. So what they do, they create those components, as I said, in the factory. And once these components have been printed, they will simply assemble it on site to erect your building structures. So they have printed many boundary walls also for using this 3D printing technology. So they have also used the similar approach of creating lattice structures using this design. During COVID-19, where there was a shortage of laborers, they printed this isolation unit using the 3D printing technology because they feel that the technology is readily available. It can work day and night without any interruption. So they printed those isolation unit and it was fitted with all kind of arrangements that is needed for a COVID patient. So they printed those isolation unit and they shipped to different states. And this is the example that already I have mentioned to you in the beginning, that this company, they have printed the breeze. And as you can see, the cross section is not entirely solid. Rather, it has been optimized to save some concrete, but still it can take the load of the application. The same company now, they feel that in a metro project, they are printing the staircase because they feel the staircase casting, it takes much more time. But in printing, with once they have the CAD model, they can simply print it and install it on site. Another company from Netherlands, they are printing more complex geometries. As you can see, the application is to print facade elements for building. So that is their core application. So the key takeaways from this presentation is that if you want to develop a material, you need to ensure the material is having isotropic properties. Then the most important point, the material, machine, and the design are interrelated in this process. And there are some challenges that still present in this technology because this technology is in growing stage. We have some issues with reinforcement, structural testings are still missing, and we have some methods that need to be developed for testing of these 3D printed elements. In terms of cost, the paper that has been published just 2 years back, So it says that when you want to play with digital fabrication, it is much more affordable when you want to print complex geometry. But if you want to print simple structures, it may be of conventional way, it is still acceptable. So our approach is that in future we'll try to identify which component of the building can be 3D printed, and we can combine these two technology, so that we'll be having a hybrid technology in the construction process, where we'll take the help of conventional casting plus the 3D printing technology to make the building more affordable and timely available to many customers. So this is the example. When I was going through a news article a few days back, I found that during this COVID time in Japan, they constructed a bridge, and due to lack of workers, they use most of the robots in this process. And they claim that by utilizing this robotic system or automation technology, they can save 30% of the building cost, and the timeline was again reduced by 20%. So with these things, I thank you everyone for attending this talk. I acknowledge all the help that I received from my supervisor and my students and staff at Singapore. So thank you very much for attending this. If you have any question, I'll be happy to answer it. Thank you very much.